Welcome to this comprehensive exploration of gear terminology and the precise language engineers use to describe these fundamental mechanical components. Today, we'll examine the critical dimensions, measurements, and features that define how gears are designed, manufactured, and specified. Let's begin by understanding the foundational concept that governs all gear calculations: the pitch circle. This imaginary circle is drawn on the gear profile in such a way that pure rolling motion on this circle produces motion exactly similar to the actual gear motion. Think of it as the theoretical reference point where two meshing gears would touch if they were simple friction wheels. The pitch circle diameter, typically denoted as d, forms the basis for virtually every other gear measurement and calculation. At the heart of gear design lies the module, one of the most important parameters in gear terminology. The module is defined as the ratio of the pitch circle diameter in millimeters to the number of teeth. This standardized measurement system allows engineers worldwide to specify gear sizes consistently. Moving outward from the pitch circle, we encounter the addendum circle, which represents the outer boundary of the gear teeth. The addendum itself is the radial distance between the pitch circle and the addendum circle, typically equal to 1 module in standard gears. This dimension directly affects the gear's strength and the depth of engagement between mating teeth. Conversely, extending inward from the pitch circle, we find the dedendum circle, which bounds the inner ends of the gear teeth. The dedendum is the radial distance between the pitch circle and the dedendum circle. Standard dedendum typically measures 1.25 times the module, providing necessary clearance between the tip of one gear's tooth and the root of its mating gear. This clearance, known simply as clearance, prevents jamming and allows for manufacturing tolerances and thermal expansion. Clearance circle. The clearance circle is an imaginary circle that passes through the tips of the meshing gear's teeth. It represents the boundary where the addendum circle of one gear meets the space created by the dedendum of its mating gear. The clearance circle is directly related to the concept of clearance, which is the radial distance between the tip of one gear's tooth and the bottom of the tooth space in its mating gear. Clearance is calculated as the difference between the dedendum of one gear and the addendum of its mating gear. This clearance is essential for proper gear operation as it prevents jamming between gear teeth, allows for manufacturing tolerances, provides space for thermal expansion, enables proper lubrication flow. The working depth is measured from the addendum circle to this clearance circle, making the clearance circle a critical reference for determining the effective engagement zone between mating gears. Total tooth depth combines both addendum and dedendum, typically measuring 2.25 times the module in standard gears. This full-depth tooth design represents the most widely used configuration in modern gear manufacturing, offering an excellent balance of strength, manufacturing economy, and performance characteristics. Tooth thickness. Tooth thickness is the width of a gear tooth measured along the pitch circle. It represents the actual thickness of the tooth material at the reference pitch circle level. This measurement is crucial for determining proper meshing between gears and affects the amount of backlash in the system. Tooth thickness is measured as an arc length along the pitch circle, which makes it somewhat challenging to measure directly. Each gear tooth consists of several distinct regions with specific terminology. The face refers to the portion of the tooth profile above the pitch surface, while the flank describes the portion below the pitch surface. The profile encompasses the complete curvature formed by both face and flank. At the very top of each tooth lies the top land, a small flat or slightly rounded surface, while the bottom land forms the valley between adjacent teeth. Circular pitch represents a fundamental spacing measurement, the distance along the pitch circle from one point on a tooth to the corresponding point on the next tooth. This arc length can be calculated as pi times the pitch circle diameter divided by the number of teeth. Circular pitch equals the sum of tooth thickness and tooth space width, both measured along the pitch circle. The pressure angle stands as one of the most critical design parameters in gear systems. This angle, measured between the common normal at the point of contact and the common tangent to the pitch circles, typically measures 14.5, 20, or 25 degrees in standard applications. The 20-degree pressure angle has become the most common choice in modern gear design, providing an optimal balance between strength, smooth operation, and manufacturing considerations. Face width, sometimes called axial face width, measures the length of the gear teeth parallel to the axis of rotation. This dimension directly affects the gear's load-carrying capacity and represents the actual contact area available for power transmission. Design rules typically specify face width as 8 to 14 times the module, depending on application requirements and mounting considerations. The effective face width accounts for real-world factors like misalignment and deflection that prevent perfect contact across the entire theoretical width. Backlash represents the amount by which a tooth space exceeds the thickness of the engaging tooth. This clearance, while essential for proper operation, must be carefully controlled. Backlash prevents jamming during operation, accommodates manufacturing tolerances, allows for thermal expansion, and provides space for proper lubrication. However, excessive backlash can cause noise, vibration, and positioning inaccuracies in precision applications. Contact ratio defines a critical performance characteristic, the number of pairs of teeth in contact at any given moment during meshing. This ratio can be calculated as the arc of contact divided by the circular pitch, or as the angle of action divided by the pitch angle. Most applications require a contact ratio of 1.2 or greater to ensure smooth, quiet operation. Higher contact ratios distribute loads across multiple teeth simultaneously, reducing stress concentrations and improving durability. Thank you for joining this exploration of gear terminology. Subscribe for more mechanical engineering insights.